In this presentation, we are going to look at the differences of random variables. So the differences can be modeled as a distribution as well. So essentially what we're interested in is the difference between random variables, normal random variables in fact. So claim amounts arising under a particular type of insurance policy are modeled as having a normal distribution with a standard deviation of 35. They are assumed to be independent of each other. Okay. So calculate the probability that two randomly selected claims differ by more than 100. Okay, so here what we're interested in is the difference of x and y. So we'll just go x minus y. So essentially it could be, is it greater than 100 or less than minus 100? Okay, so there's two scenarios there. X is greater by 100 or y is greater than by 100. So essentially we'll just, in the context of D, we'll keep D consistently x minus y. We'll look at two scenarios here. X is greater than 100 or less than minus 100. Okay. So D, they always have an orientation of x minus y, one minus the other. So just to keep it simple. Now you might notice that we're given the standard deviation, but we're not given the means. Okay. But the means are both they have the same mean essentially. So the expected value of the differences, mu of D, is mu of x minus mu of y. Mu of x equal to mu of y, so that's equal to 0. Okay. Now the variance of the differences is essentially sigma x squared plus sigma y squared. So we add the variances when we get looking at the differences. Okay, so just don't forget that. So sigma squared d equals sigma squared x plus sigma squared y. Okay, that's a little trap there. Okay, so don't like, it's minus up here. Okay, mu x minus mu y, but we always add variances if for differences or sums. Okay, so that's where we get 2 times 35 squared. So the sigma x and sigma y are 35 squared each. Okay, so twice that, 2 plus 2, 35 squared plus 35 squared. So essentially this is what we end up with. D here, this is what we end up with here. D is normally distributed with a mean of 0 and a variance of 2,450. Okay, so okay, I paused there for a second. I'll just pick up where I was. I just had a little technical issue. So this is what we're asked here. The probability of D being greater than 100 plus the probability of D being less than minus 100. Okay? So those are the two things we're looking at there. So essentially we can recombine them into one expression here. The absolute value of D being greater than 100. Okay, just look at it from the point of view of the absolute value. So that's how we get here. Okay, that's where this absolute value comes in. So using the z-score expression, and remember, recall and notice that we're using the absolute value of z there. That is the z-score there, 100 minus 0. Remember, the expected value of the differences is 0 divided by the standard deviation, which is the square root of 2450. And that is a z-score, or the absolute value of the z-score is greater than 2.020. Okay, so essentially what we have down here is, and I'll just go down here a little bit further, the probability of the absolute value of z being greater than 2.020 is equal to the probability of z being less than minus 2.020 plus the probability of z being greater than 2.020. Okay, now these, by the symmetry rule, these numbers are actually equal to each other. Okay, so essentially that's why we have here 2 times 0.0217. Okay, so that's just a sort of look one of them up at the tables. Just recall, recognize that what we're using here is the symmetry rule. and then we work that out, and it is 0.043. Okay, so the absolute value thing, really, you might sort of think of that's actually quite hard and unexpected. It's actually not really. It's actually, you can manage it fairly easily, okay, once you employ the symmetry rule. Okay, so I think that's it. Yeah, that's straightforward enough.